this video, we are going to talk about one of the cornerstone results that make scale relativity be called scale relativity. So why do we use this term scale relativity to describe non-differentiable physics? That's what we are going to talk about today. So the core result of scale relativity, on which it is based actually, it is that if you take a non-differentiable curve, the length that you can define on this curve is explicitly scale dependent. And that's what we want to explain a bit in more details in this video. So basically, what we mean by scale dependent is actually fractality. That's why we are talking about fractal spacetime in the framework of scale relativity. So we are going to talk about why non-differentiability implies fractality. But here, fractality, really, we mean in the sense of explicit scale dependence. Explicit scale dependence. Like of length, but it can be also anything. That's what we mean by fractality. It's something that is a bit more general than just self-similarity. The self-similarity, that's what we are used to talk about when we talk about fractals. When you zoom in, you see the part of the fractal has the same structure as the wall, right? Here we just really mean explicit scale dependence. So let's start it. Let's consider a non-differentiable function, okay? Like this. So x, f of x, and the graph of a non-differentiable function is something very wiggly. You cannot define any tangent line on it, okay, like this. Let's say now we are interested in measuring the length of this curve. What we know first is that the length of a non-differentiable curve is not going to be a finite quantity. It's going to be some kind of non-convergent value. You can only define a finite length for differentiable curves. Okay? So let's see how that works. Let's try to see if we cannot still define a concept of a length, like some kind of intermediate concept. Let's see if we can define the concept of the length measured as at a given scale. Let's see what it means. So let's write down here this point, this coordinate xa, and this coordinate here xb, as being the x coordinates of the point here A and point B here on this curve. Okay, so let's start. We want to give a definition kind of the length of the curve at first, so length at resolution scale epsilon 0 is equal to xb minus xa. Okay, xb minus xa. What will be the definition of the length at that resolution, at that scale? It's going to be simply the length of the segment joining A and B. This. That's going to be the length of the curve at resolution epsilon 0. And let me be a bit more explicit. I'm going to write it down as L as a function of the resolution. Okay? Now you repeat the same. So that's the first point. You do now the length at scale epsilon 1 is equal to, now you take the half of this. You take epsilon 0 divided by 2. What you can do is that you can find any point close to the middle of that interval here, xa and xb of that interval, you can find a point as close as you want to the middle. Let's call it x 0, 1, such that when you compute, when you look at the point that is associated, let's call it C0, 1, when you compute the length of the curve at that resolution, you compute it as taking the segment from A to C0, oops, very straight, C0, and then from C01 to B. And this length is going to be, of course, bigger, strictly bigger than the first. So what you get is that the length at resolution epsilon 1, it is the sum of A C01 plus the segment C01B, and this is strictly greater than the length at resolution epsilon naught. And this is strictly because of non-differentiability. Okay, so you can always find such a x coordinate in the close to the middle of xb minus xa, such that the length of the curve measured at that resolution is bigger than the length of the curve measured at the previous resolution at a higher scale. And here the length is just a covering with straight lines. We compute it like that. We cover the curve with straight lines associated with the resolution that is given. Now, if we repeat this many times, we understand easily that we are going to get a length that is bigger and bigger as the resolution gets smaller. So let's do that. So now the length at resolution, let's do it once more. The length at resolution epsilon 2, so as epsilon 1 divided by 2, and then epsilon 0 divided by 4, we can also find a point in the middle of xa and x01, close to the middle of xa, x01, let's call it, I don't know, x11, and then a point in the middle, close to the middle of x01, xb, let's call it x12, such that when you get to a point here, let's call it C11, and here C12, and that you compute the length at that resolution epsilon 2, then you cover your curve with lines like this, then like this, then like this, and then like this. You get a length that is again bigger, strictly bigger than the first. So again here, let's write it down explicitly. The length measured at length scale epsilon 2 is just A C11 plus C11 C01 plus C01 C12 plus C12B. And this is strictly greater than the length at the previous resolution scale. So we can, in general, say that the length at epsilon n plus 1 is strictly greater than the length at epsilon n for all n. And this fact, combined with the fact that the length of a non-differentiable curve is not finite, leads us to write down that the limit as epsilon goes to 0 of L of epsilon goes to infinity. In other words, the concept of the length of a curve that is non-differentiable doesn't make sense in the limit where we take the resolution scale to be small, going to 0. Okay? And here is really the key idea of the scale relativity theory. is that if we want to introduce non-differentiability in physics or in geometry in a general way, how can we talk about the usual geometrical quantities, position, velocity, and so on, area, volumes? Well, what we do is that we don't take the limit as epsilon goes to 0. We just leave epsilon being a variable. And we take then the length, the volume, the area, any quantities, we let them be dependent on the resolution scale, right? So instead of having any quantity, let's say f of x, you now have a quantity which is not defined as the scale goes to 0. So we leave it as a variable. We leave it fx of epsilon. So the scale is explicitly put in the description of the quantities we are describing. Okay? And this is the important point on how we can still keep the previous tools of differentiable physics, which are differential equations. The thing is that this dependence on epsilon can now be taken as a smooth dependence on the resolution scale. So the way, basically, the way the divergence, the way the quantities diverge as epsilon goes to 0, we don't know about that. And so the knowledge of that can be obtained in the scale relativity theory as a solution to a differential equation, but in the space of those resolution variables, right? So we have both a dependence on the usual variable, x, t, and then a dependent on the scale variable, which is basically the interval, okay, the resolution interval in that context. Let's see how this already appeared in what I did in the previous video, when I did the derivation of the Schrödinger equation. As you remember maybe, I wrote down that the non-differentiability hypothesis is taken in the derivation of the Schrödinger equation as the replacement of the usual relation between displacement and velocity, that is usually in classical physics dx is equal to v dt. This is replaced with the doubled displacement element, like this, v plus minus dt, which is the differential part, plus the square root, wait, I forgot the stochastic variable, plus the stochastic variable, d plus minus, square root of 2d absolute value dt. Okay? Now, this means that if you want to define, let's say, the velocity of the process, okay, the velocity of the process, d plus minus x over dt, you're gonna get v plus minus, which is well defined, okay? It's a quantity that is defined for all values of dt, plus something, and it should be a plus minus here, that is explicitly dependent on the resolution variable here, dt. This is the epsilon here, okay? So by doing that, we really can write down, if we say that this is v tilde plus minus, it is then equal to v plus minus, which is differentiable, plus some kind of, let's say, w of epsilon. That is scale dependent on epsilon. Okay? That's what it is. So we can really see that here this quantity d plus minus x divided by dt is explicitly scale dependent. Okay? And actually this solution is solution to some scale differential equation that we have still to discuss about, right? And that's what scale relativity is about, to find the right laws describing the right scale dependency of some or the fundamental laws of physics, basically. Okay? And the laws that you can allow, they are restricted by the principle of scale relativity. Okay, we cannot just have any kind of scale dependency. The scale dependencies that we can accept are the scale dependencies respecting the law of scale relativity. And that's what this video was about, to show how non-differentiability implies scale dependence of quantities. Okay, the right way to describe non-differentiable things is by introducing those quantities as being explicitly dependent on the scale of observation. Thank you for watching, and I hope you enjoyed.